Exceptions. Of course, there have to be exceptions to the rules, right? There are different types of exceptions to the octet rule. One is odd-electron species. These are molecules or polyatomic ions that have an odd number of electrons. You cannot satisfy the octet rule with an odd number of electrons. It's just not possible. These are called free radicals, and you've probably heard of that in just popular news and stuff. They talk about free radicals. Those are not good for you. They're very reactive, they're not very stable, and so they can cause problems in your body. So these are molecules and ions that have an odd number of electrons. So let's draw the Lewis structure for one of my favorite molecules. No! NO. That's shouting, right? All caps. No. So it's a diatomic molecule. There's nothing confusing about how to connect them. How many valence electrons do we have to work with here? 11. 5 plus 6 is 11. Well, we put a bond in there. That's 2, 4, 6, 8, 10, 11. Well, nobody's happy. Let's see what we can do. How about if we take this lone pair and share it? Well, that's better, right? So here we have the oxygen obeying the octet rule, but the nitrogen only has 7. 2, 4, 6, 7. What if we put that odd electron on the oxygen instead? What if we did it like this? Now the nitrogen's happy and the oxygen isn't. Lewis' model says this is not a good molecule. But nitrogen monoxide does exist. It's present in air pollution, and one of the reasons it's harmful is because it's not very stable, and it will tend to react with lots of different things. So what do we do if we have an odd number of electrons? You just do the best that you can. So we've got 2 different things here. Which one is better? Formal charges. Formal charges. This oxygen has 2 bonds and 2 lone pairs. It's going to have a formal charge of 0. Because oxygen has 6 valence electrons, and if we split this up, it's going to get 2 electrons from the bonds, plus 2 is 6, and so the formal charge for that one is 0. What's the formal charge on the nitrogen? 0. Nitrogen has 5, and in here it has 5, and so that's 0. Let's look at this one. Here, what's the formal charge on the nitrogen? -1. Nitrogen has 5 valence electrons. In this molecule, it owns 6, so it has a -1. And here, the oxygen has a +1 formal charge. So this is the best Lewis structure. It violates the octet rule. Any questions? Another way that we can violate the octet rule is by incomplete octets. We got an even number of electrons, but we don't have octets. Boron, let's see boron on the periodic table, element number 5. He's one of the little guys. Boron often violates the octet rule in this way. So this is saying, let's draw the Lewis structure for boron trifluoride. Well, let's probably put boron in the middle and the fluorines around it. Remember, the more electronegative element is often terminal. And so fluorine is very electronegative, and so we'll put him terminal around here. How many valence electrons do we have? 24. 3 for the boron, 7 each for the fluorines. So I've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Is everybody happy? Not according to the octet rule. The fluorines are happy, but the boron isn't. So normally what we would do is we would take a lone pair and share it, right? What are the formal charges on each of these atoms right now? They're all 0. Fluorine has 7 valence electrons. In this molecule, if we break all the bonds and divide them up equally, each of the fluorines has 7. 0 formal charge. How many valence electrons does boron have? 3. And in the breakup, it would get 3. It has 0 formal charge. If we make a double bond, these fluorines are still 0, but now what's the charge on this fluorine, the formal charge? 7 minus 2, 4, 6. So this now has a +1 formal charge, and the boron ends up with a -1, because it had 3 and now it's got 4. So formal charges tell us, no, the first way was correct, with boron only having 6 electrons. It violates the octet rule. Now, boron trifluoride will tend to react with other things in a way that will complete the octet on boron. So it's not that boron never has an octet, but it will sometimes violate the octet rule. And the only way that you can tell if it's going to do that is by looking at the formal charges. Beryllium also tends to do this. Yes?
Looking at the formal charge is bad.
Mm-hmm.
How would you find formal charge for the fluorine on the bottom? You just cut it in half?
Yeah, you just cut this bond, and then we say, well, fluorine has 7 valence electrons, and then we count up how many it owns in here. 2, 4, 6, and 1 from the bond is 7. 7 minus 7 is 0. Okay? So it's the smaller elements that tend to do incomplete octets. Then we have the opposite, expanded octets. They're more than 8. This can happen in elements that are in period 3 or larger. They can expand their octets up to 12 or even 14 electrons instead of 8. The reason they can do that is that there are 3d orbitals available. And so the electrons can move up from the p into the d orbitals, and that makes more room. Let's do arsenic pentafluoride. Well, we'll put the arsenic in the middle, and we'll draw the fluorines around it. I'm going to squeeze 5 of them in there. And you might say, well, why don't you bond a fluorine onto a fluorine, make some chains? Well, you can try that out, but you'll find that formal charges are going to tell you that that's not good. Okay, so made this little star-shaped thing. Let's look at number of valence electrons. Arsenic has 5, and each of the 5 fluorines has 7, 35, 40. So I've already got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40. I counted wrong. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Oh, see what I did there? I got a little carried away. There we go. What are the formal charges? Well, all the fluorines are going to be 0. How many valence electrons does arsenic have? 5. How many does it get in the breakup of all these bonds? 5. This is good. Anything else you try that will obey the octet rule is going to give you non-zero formal charges. Let's do sulfur hexafluoride. Sulfur in the middle. Six fluorines. Six fluorines times 7 plus how many for the sulfur? 6. So that's 48. I'm going to spare you listening to me count. If you don't believe me, you can count them yourself. What are the formal charges? They're all 0. Sulfur has 6 valence electrons. If we break these bonds evenly, it's going to have 6 valence electrons. Formal charge is 0. Any questions? Yes?
You said something about beryllium forming a bond. I thought it was like 100.
Yeah, beryllium is over there with the metals, but sometimes beryllium forms covalent compounds. That's part of the lying we do. We simplify things and generalize things, and then we get caught. Any other questions? Okay, so let's look at sulfuric acid with and without an expanded octet and examine the formal charges. Well, when we get to these things that have more atoms in them, it becomes a little more complicated to think about how the heck are we going to put these together. Symmetry is often helpful, or at least a good place to start. So I'm going to start with the wrong marker. I'm going to start with sulfur, and I'm just going to stick the 4 oxygens around it. And then I'm going to stick the hydrogens on the oxygens. Because we're supposed to do with an expanded octet and without an expanded octet. If I put the hydrogens on the sulfur, that's obviously going to be expanded, so I'm not going to do that. We have to total up our electrons. We have 2 from the hydrogen, we have 6 from the oxygen, and we have 24 from the 6 from the sulfur, 24 from the 4 oxygens. I believe that's 32. So in my bonds, I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. We say, yay, beautiful. Obeys the octet rule, awesome. What are the formal charges, though? Well, the hydrogens are 0. Let's start in the middle. Sulfur. Sulfur has 6 valence electrons. How many does it get in the breakup? 4. That gives it a formal charge of +2. These oxygens are going to have the same formal charge because they have the same number of bonds and same number of lone pairs. Oxygen has 6 valence electrons. In the breakup, it gets 2, 4, 5, 6. That one's 0, this one's 0. But these oxygens are not going to be 0. They're going to be -1. And we say, well, the negative charge is on the more electronegative element. What's the problem? Sulfur is in period 3. Sulfur can expand its octets. On the 3rd floor of the Quantum Hotel, we have another room with 5 beds in it. We can take those electrons from the 3p level and bump them up. Okay, so let's look at that. How could we reduce the formal charge on sulfur? The problem is it should have 6 electrons that belong to it in the breakup, and it only has 4. We could take the octet from this oxygen, not the octet, a lone pair, and share it here. So let's draw this again over here. Sulfur, oxygen, hydrogen. So we don't want to mess around with these oxygens or these hydrogens. They're 0. We want to leave them alone. But the problem here is that the sulfur really needs to have 6 electrons that belong to it. We can't give it a lone pair because then the oxygen wouldn't even have an octet. But we can take a lone pair and stick it down there. See what I did? I took this lone pair up here and I made it another bond. What's the formal charge on this oxygen now? 0. What's the formal charge on the sulfur? +1. We're going in the right direction. We fixed the oxygen and we made the sulfur better. So let's do the same thing with this oxygen and take a lone pair and make it a double bond. Now the sulfur has 0 formal charge, and this oxygen also has a 0 formal charge. This is the correct Lewis structure. Formal charges help us to understand that. Just following the octet rule is not going to work. So this is important. We can expand octets to lower formal charges for period 3 elements, or higher, but we're just not going to run into them. Period 2 elements never have expanded octets. In the Quantum Hotel, in order to do this bonding thing, you can move electrons into another room on the same floor, but you can't move them up to another floor. On the 2nd floor of the hotel, there's only 2 rooms. Oxygen already has electrons in the P room. It can't move them out anywhere, and so it never does an expanded octet. Sulfur, selenium, tellurium, they can do that because they're bigger. Any questions? Okay, so let's practice writing Lewis structures for compounds having expanded octets. Xenon hexafluoride. What's weird about this molecule? It's a noble gas. Trippy. Noble gas forming a compound. Well, we want to put the more electronegative ones on the edges, right? Terminal. So we'll put xenon in the middle and connect the fluorines around it. Now that we're getting a little better at this, I like to just draw single bonds in to connect things first. And then I just remember to go back and count them. So how many valence electrons does xenon have? 8. And we have 4 fluorines, and they each have 7. So 28 and 8 is 36. So I've already got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. We've never had this happen before. I have more electrons than I need for the octet rule. I need to put 4 more electrons on here. Where am I going to put them? On the xenon. Xenon's a big guy. He's a period 3 or greater, so he can handle it, and so he's going to get 2 lone pairs. Yes?
And it doesn't matter where we put the double bond back, right?
Pardon me?
It doesn't matter where we put the, oh, never mind.
Put the lone pairs?
Yeah.
It doesn't matter where around the xenon that you draw them, no.
You can't put one down.
You don't want to separate them. You want to show them in pairs. You don't want to put one here and one there. But if you put them, you know, if you move this one up here, it's not a big deal.
What shape was that?
That's coming up. What shape would that be? It's going to be square planar.
It'll pop up in the middle, right?
So it's kind of like fancy, but for like a
We'll get to it. I'm glad you're excited about it. We'll get to it. Are there any formal charges in this molecule? Hopefully we're beginning to recognize fluorine is a halogen. The halogens like to form one bond. It's got its octet, so we can just know that those are 0. Xenon. Xenon has 8 valence electrons. How many does it own in the molecule? 8. 0 formal charges. Seal of approval. Okay? Let's look at phosphoric acid. So we'll put the P in the middle and put the O's around it. This is looking a bit like sulfuric acid, isn't it? Where do you think we should put the hydrogens? Maybe try sticking them on the oxygens, huh? And then let's count up some electrons. We've got 3 plus 5 plus 24. Did I do that right? I didn't bring my calculator. So we're counting to 32. 2, 4, 6, 8, 10, 12, 14. 16, 18, 20, 22, 24, 26, 28, 30, 32. Awesome. Looks good, doesn't it? What do the formal charges say?
It's off.
It's off. How many bonds does oxygen like to make? 2. This one only has 1 bond. If you do the formal charge analysis, this oxygen is 0, this one's 0, this one's 0, the hydrogens are going to be 0, but this oxygen is going to have a -1 formal charge. And the phosphorus is going to have a +1 formal charge. So what we'll do is we'll do what we did with the sulfate. We'll take this lone pair and bring it in here. I'll just take this one actually because it's up in the writing. And we'll bring it in here. That reduces the formal charges of phosphorus to 0 and oxygen also to 0. And so this is the correct Lewis structure. Any questions? This is the stuff we didn't tell you about in Chem 3A. We said it exists and we left it at that.